Hello everyone, welcome once again to a TVS colloquium. Today we have Kendall Ackley, who is an assistant professor at Warwick University working with gravitational waves. And today she will tell us everything about GOTO. So Kendall, please take it away.
Hey, great. Just thank you very much for inviting me to give the colloquium today. I'm happy to present on the work we've been doing with the gravitational wave optical transient observer, which is a wide field instrument which is dedicated to gravitational wave follow-up events, as well as a variety of fast transients. So just to kind of preface where we are, we're so-called in the era of multi-messenger astronomy. And this had been kind of working its way up, over the few decades prior to the first gravitational wave event. But this is kind of the very first time where we're repeatedly looking for signatures in multiple multiple messengers, right? So we have gravitational waves, we have information that can come from cosmic rays, neutrinos, gamma ray events, and they all sort of interact and give different pieces of the types of events that we're looking for in a variety of different ways. And so some of these can be observed simultaneously. Some of them will come at different delay times. So since 2015, there have been over, I think the new gravitational wave catalog is soon to be released from within LIGO. But I think it's now well over 200 events, give or take, where from the first gravitational wave transient catalog 3, there were only 90. So there's been an extreme growth in the number of gravitational wave events in particular. And in the last observing run, so-called the 04 run, which started in 2023 up until the end of 2025, there were thousands of events, hundreds of significant events. But, of course, the challenge is that there's still only one, bona fide confirmed case where there was a gravitational wave event and photons or some other messenger signal that was accompanying it. And so, there could be lots of reasons why this is challenging to continue to make multi-messenger detections with gravitational waves in particular. One of them is just through how we detect gravitational waves themselves. These are what I would consider to be one of humanity's greatest engineering feats. These are the most sensitive instruments ever built. And what they do is they measure the change in the length scales down to 10 to the minus 20 meters in length change. And the way that they identify gravitational wave signals is that by measuring these length changes, it induces a photon response on the light detector. And so in a normal situation, without any passing gravitational waves, you don't get any signal. And when a gravitational wave passes along these arm lengths, you get some signal that modulates with the gravitational wave waveform that you expect. And so this is one of the particularly interesting gravitational wave events that was detected. And you can see that not every gravitational wave interferometer will be as sensitive to the signal. And it just depends on where the signal is coming from in relation to the orientation of the interferometers. And then as well as timing information between these interferometers, it can be very challenging to not only localize them well, having precise timing, as well as fitting waveforms. So the reason why we don't necessarily continue to have solid gravitational wave events with other signatures is a myriad of different ways, but it's a fascinating challenge nonetheless. And so just to kind of go through this in more detail, so we have some current challenges in just that neutron star mergers themselves are a bit rarer than black holes. So we have one solid candidate of a binary neutron star event, that's 170817. There are other candidates that are similar in confidence, but without we know that this was a neutron star binary merger. But we can see based off of this figure in the top left that we're vastly over detecting binary black hole events. And so are these rare astrophysically, or is there some other challenges that must be met? And then on the top right here, we also know that search localization areas can be tens to thousands of square degrees in extent. So the phenomenal 1708-17 event got down to about 28 square degrees, whereas when we're looking at this GW 2305-29, the 90% contour probabilities was basically the entire sky. Not only that, but we're looking for signals that are decaying rapidly over a few days. This is in the lower left corner, as well as them just being these kilonovae sources that are thought to accompany these gravitational wave events. They're just intrinsically faint, on the order of 18th magnitude or so. And not only that, so not only are they rare, they're hard to find, they fade quickly and they're faint, but they're also plenty of other transients which act as contaminants. And so we have in this sort of phase space here, in this lower left corner, to really distinguish between these different types of events is quite a difficult challenge to overcome. Okay, so here we have, this kind of motivates the design and philosophy of why Gravitational Wave Optical Transient Observatory, so GOTO, why this was built, and the philosophy behind it. And so this was first proposed in 2014, with the main idea being to build a dedicated facility for the electromagnetic follow-up of gravitational wave alerts. And so the design was for rapid wide field searches of exotic transients, but particularly focusing on gravitational wave EM counterparts. And just to note again that this is really built as a dedicated facility for the EM follow-up, but just in the pursuit of looking for these types of signatures, you're going to get exotic transients, hopefully and potentially along the way. And part of the design philosophy was also the aim to catch counterparts early. And so this was mainly thought of as almost a feeder facility. So as we make the detection early, and then we pass those detections on to other facilities who can perform the deeper follow-up. It was also meant to be built as a modular network. And so here we can see the design where we have a single mount, and on this mount we have 8 what we call unit telescopes. And what they are is they move almost as a unit altogether, but this also means that they can be staged in different deployments, and they can be scaled in different ways, and they're also adaptable. And so here you can see per each site you have 2 domes with 1 mount in each dome with these 8 telescopes, and these operate independently. The design philosophy was also to use off-the-shelf hardware. And so this meant that when we're ready to deploy, we can get the hardware as needed. And so not only does this mean that we can deploy faster, but we can also keep the project very cost effective. And so I think in relative terms, it's quite a cheap instrument when you think about it in these terms of using off-the-shelf hardware. And the main design philosophy was that the entire network should be autonomous. And so the full automated control systems and the analysis pipelines should be fully autonomous. And this removes a lot of the subjective interference that humans can deliver into doing targeted follow-up. And so, of course, you always have this trade-off between cadence, area, and flux. And so the idea was to sort of maximize where we fit on this phase space, which is that we sort of went more towards collecting as much area as fast as possible. So sort of along this line. And the follow-up facilities would be more towards gathering flux. Okay, so just going through sort of how GOTO has been developed and how it was staged and evolved over the past couple of years. So our first prototype we had first light in 2017. And then we had several staged evolutions over these phases. And so this eventually allowed us to work in these incremental steps so that we could finalize our design. And so this was done during some of the early LIGO runs, so 01 to 03, but that we wanted to make sure that we operated almost like the LVK itself, where you do maintenance and then the observing run, and then you do maintenance and improvements and upgrades. And so our first prototype we considered to be sort of in the stable phase was in 2018. This consisted of 4 unit telescopes. We upgraded in 2019 to have 2 extra alternative telescopes here that were on the outside. And then we upgraded those again in 2020 with some other final upgrades. And so sort of details about these telescopes is that they're 40 centimeter what we call unit telescopes. They're fast, so they're f/2.5. There's room for a 5-slot filter wheel, and we use these Botter L RGBC filters where C is clear. But we're primarily operating in the L band, so this is a really wide 400 to 700 nanometer wavelength. And we're getting about 5.5 square degrees field of view per unit telescope. And we're operating still with CCDs. So these are the FLI microline cameras, about 50 megapixel CCDs. But we have plans to upgrade, which I'll discuss at the end. So even though we were sort of incrementally evolving our systems and doing these commissioning and upgrades, we were still participating in these, not only in the scientific runs from LIGO, but also with other triggering and alerting experiments like GRBs. So we had all sky coverage from March 2019 to August 2020. And so here's a figure on where we were sort of at that time frame. So here on the bottom, you can see the number of times that each tile of the full sky that we had observed. And there are a couple of hot spots here that related to certain events. And so you can see sort of as we evolved over time that the coverage also was changing. So you can see that we have a fixed sky grid of overlapping tiles. And so when we are performing our gravitational wave follow-up, we were overlapping the sky maps onto those tiling grids and performing our follow-up. During the first half of O3A, we triggered on 32 events. And so that's written up in Gompertz et al. In 2020. We also triggered on 93 Fermi GRBs. And so this was a PhD student of mine, Travis Mong, who worked with sort of doing this dedicated wide field rapid follow-up in the absence of gravitational wave triggers that we could follow up. And here you can see the outline of how this evolved over time. So in the center, in this black bar, is our 4-unit telescope setup. And then here's the addition on the outside, the UT5, 6, 7, and 8. And you can see that the change in our approach and the change in the telescope hardware that we applied, that we managed to get a slightly larger field of view. Okay. During that time, we also were going through upgrades where we settled on our final design, or we thought we had at least a progress. So we found a new vendor. So we went through ASA. And so we managed to get our second mount installed in the second dome on La Palma. And so this was a huge performance upgrade for us. So not only did it help with a lot of our mount stability issues that we had seen during the prototype phase, it helped with wind stability. Our PSF performance was remarkably improved. And this was just due to some sort of major design changes, mainly that we had closed our tubes up where previously they had been open. We improved our direct drives on the mounts. We improved some of the optics. And so what we ended up gaining was about a factor of 2 in latency improvement between slewing, as well as a factor of 2 increase in our survey volume rate. So this was a huge improvement for us. And then in November 2021, we continued with saying we liked this design. It was performing very well. And so we completely dismantled our previous prototype and we replaced it with this new setup and this design. And so once this had been completely dismantled and deployed, we considered GOTO-North to be in its deployment or so-called final design stage. It was definitely a challenge at many times. There was a lot of things going on. But primarily is that we had chosen, I think, the best time in the world to perform these commissioning feats, which was during an active volcano on the La Palma Island. So here you can see us working and dashing in and out as the volcano would rumble. But we managed to work through, and we got the facility on site and on sky in the end. So yeah, not only did we have the volcano that had been erupted, but we also were dealing with delays and pandemics. We were dealing with ice storms, firestorms, and so it was quite the feat, I think, to get it going. But still, we managed in the end. And then in November 2022, we started working on our GOTO-South site. So this is located at Siding Spring Observatory. In November 2022, we constructed the pads and the domes. Following about 6 months later, we installed both mounts and all 16 UTs. And so this was a huge effort. We did this in about 6 weeks. And this was primarily motivated that LIGO was starting the O4 run in May of 2023. We knew the final design. And so we went to the Siding Spring Observatory and basically built this from the ground up, starting with the empty domes. We were on sky and observing, but we weren't able to take the data off at the time, but we were able to improve our networks and perform the network link and upgrade that, and then connect that to our central scheduler, where then we can pull the data. So we would say that GOTO-South was in its final commissioning and was finally commissioned and on sky in June 2023. And so now here we have the full GOTO network. So this is since 2023, we have been completely and fully operational. All 4 telescopes are fully autonomous. They operate in an independent mode. So here you can see we have the 2 dome site up on La Palma and the 2 dome site down on Sighting Spring Observatory called GOTO-North and GOTO-South. Each node has 16 unit telescopes. They cover approximately 90 square degrees. Together as a site. The full telescope network is a total of 32 telescopes, which gives us about 180 square degrees instantaneous field of view in the small gap where both La Palma and Sighting Spring might be visible to the same sky. We survey the visible sky about every 2 to 3-ish days. So it's about 10,000 square degrees per night. And we're producing about 4,000 images per telescope each night. So that's about 2 to 5 terabytes of data products every 24 hours. And so this network, it really is operating 24/7. So basically, as soon as La Palma closes its domes, Sighting Spring starts its observations. So it's really this continuous 24/7 operations, which produces its challenges in and of itself. Here is the design of the field of view when it compares to other facilities to give a kind of a sense of where GOTO lies within the landscape. So the array design allows this large field of view because you can see we do this slight overlapping of our unit telescopes along the sky. And so this allows us to find candidates which may be on the edge to then be picked up by another unit telescope as a way of confirmation. But each dome and each mount is practically independent, but this allows us a lot of flexibility. So not only can we choose to cover large patches of the sky rapidly, which each one targeting its own part of the sky, or we can double them up and gain in depth. We do leave the option for colored filters, but as I had mentioned previously, we're primarily sticking with the single L band, which is the wide. It covers green and red together. Okay. And so I just wanted to say that it is a large collaboration, a very vibrant collaboration, and a hard work of plenty of us. There are over 70 members within the GOTO collaboration. Here's one of our science meetings, and it is the work, while it is led out of the University of Warwick, with the PI being Danny Stiggs, it is without a doubt the efforts of everyone involved, and is particularly in this photo, who helped to get us to where we are today. Okay, and I just want to transition over to some of the details. So this is the software infrastructure that we have in place. So what we do, and I'll try to go through this a bit quickly, but what we have is a gravitational wave alert will come through, or any particular gamma ray burst event or neutrino alert. They'll come through, they'll parse as notices, and then it works its way through our kind of software stack. And so it gets processed through what we call the Sentinel. The sky map gets mapped onto the tiling grid, which then gets sent to what we call the scheduler. And the scheduler organizes how we perform our follow-up given some of the logic that we had set in advance. And I'll go through the follow-up strategies that we have in place. So the scheduler then sends commands to each one of the telescopes, which then act as independent operators. So then the images, once they're taken, are transferred back to the University of Warwick, where they are performed, where they are calibrated, and the imaging processing pipeline has been performed on it. And so what we get are science images. We have a stack of reference images to produce the difference imaging processing to produce source candidates. And from there, we pass that on to what we call the GOTO Marshal, where we can perform our candidate vettings. And from there, we can either send it to our citizen science group, who is also a very vibrant community, or we pass it on to other facilities, either through TNS reports, GCNs, or through our programs that we have in place. So just some details about the telescope control system that we have in place. So this was mainly developed by Martin Dyer, who's at the University of Sheffield. This basically runs through that this is the sort of autonomous orchestrator of all of the facilities. So all 4 telescopes, again, are fully autonomous. Once we receive the alert, it begins automated processing of the alert itself. The telescopes then receive the targets once the central scheduler has mapped the strategy onto the alert, given our logic. And then we receive information on Slack, such as, has the pilot started up okay? Are all the conditions okay? Or were there any faults in the instrument? And if there's a particularly interesting alert, should we wake up and respond? There's also web dashboards for monitoring with webcams, weathers, target cues, etc. So here is the scheduling and strategy side of things. So this has very bespoke logic, and it depends on the type of alert that comes through. And so what handles this as the orchestrator is the sentinel. And so the sentinel will monitor each of the alerts and then determine either both the strategy that we apply as well as a rank. So whether or not it should override any new alert that has come in. So take, for example, this tree, this decision tree. So this was sort of the end of our LIGO EM follow-up run. What we have is an alert will come through. If it has a particular coincidence marker with it, it gets the highest rank. And this Raven external coincidence detection is basically saying that a GRB has been found in coincidence with the gravitational wave event, and that we should wake up and make sure that the data being taken is of the highest quality and all the processing is fine. Then what we can say is classes about what our believability of the signal. So is it significant? What's the false alarm rate? Are there any other metrics that we can pull in? If that passes our thresholds, then we pass through and we say, okay, is it bright enough for what we expect? So is there a possibility that it has a neutron star component? Is it within a distance horizon? If it passes those criteria and it's significant again, then we say, okay, definitely wake up and make sure that this event is followed up. And so these would be particularly interesting events that maybe don't have a GRB coincidence associated with it, but that could also happen for a variety of reasons. Maybe one of the gamma ray facilities, had some data collection issues, just that needed to also be looked at by humans. So that gets a rank of 2. If it's not significant, then it gets a rank of 3. And then we downrank again by how quickly we can tile it. Some similar logic applies to the GRBs. It's slightly different, but we do have, it follows the same sort of strategy where we apply conditions. Okay. The automated pipeline itself. So this was a recent paper by Joe Lyman, who led this work. This is the Cadmos pipeline. So what we have is the raw exposures are transferred to the University of Warwick, where we process everything at the university. Everything is processed using, Apache Airflow here, and then it's run through Celery to schedule and process them. So each image is calibrated individually, and then what we do is we then stack sets of these, what we call single images together to create a deep stack. For gravitational wave follow-up, that's about 4 by 90 seconds. Goes into the stack. For GRB follow-up or for others, it's 4 by 45 seconds. The archival template images are then used for the reference. So these were dedicated, high quality. We went through each one of these template images to make sure that they were of the highest quality. And so then we use these to perform our difference imaging with an example here. Then what happens once the data has been processed, we pass it on to a real-time candidate vetting, and this is what we call the GOTO-Marshal. And so this is sent to the internal sort of page where we can perform vetting and classification. And it has a lot of logic again behind it, where we cross-match against a lot of known catalogs. So just, is it a minor planet? Is it a known Gaia source? Is it a known variable source? Does it already exist on the TNS? Are there historical photometry from other facilities? What about historic GOTO data as well? Once all this has been passed on, what we can see is that then the candidates receive contextual classification. And so this is handled by a package that we call Moriarty. This is by postdoc at the University of Warwick, Tom Killerstein. So this is where we have a candidate event that has come through. It has been associated with potential host galaxy. This host galaxy was identified in Glade Plus with probability of connection. And so it gives a lot of contextual information on whether or not we believe this event, given all this other information that we can gather through the public realm and through public queries. And also as part of this is that we have buttons for we also have buttons for automated reporting to both TNS. We also have buttons to sort of draft up GCNs that we can submit. And we can also trigger follow-up for facilities that we have time on, particularly the Liverpool telescope or PT5M, which is just up the road from us on La Palma. I think an interesting aspect to this is that some of these candidates, while they do make it into the Marshall, we also upload our candidates through to Kilonova seekers. So this is a way to get already sort of public access of potentially interesting transients that have been processed through GOTO. This is done through the Zooniverse platform. It's a web interface that you can pull up on your browser or on your phone. And there's been quite a lot of discoveries so far. So one of them in particular was AT 2023 POF. This was first discovered by Kilonova Seekers volunteers. And on the TNS report, we made sure that they got their credit, that they were listed on the discovery, that they were correctly identified that this was an interesting event. There was also dwarf novae discoveries, which led to a couple of publications, which also included the volunteers who participated. So that was very fun for them and very, I think, rewarding for the volunteers who were present to be part of academic literature and to be a part of the discovery of events. Okay, so I just wanted to go briefly now through sort of how the technical structure of GOTO works. So we're split into two types. We have science working groups, and we also have the technical working groups. And so these are built, structured over a few topics. So the main one, which is our main core science driver, is the gravitational waves and kilonova follow-up. And so the PI, Danny Stiggs, and myself, we lead the coordination of that. We also have a GRB working group, supernovae, host galaxies, TDEs, variable stars, asteroids, and neutrinos. And so if you're particularly interested in one of these types of events, or in this particular science case, I left the names up for you to be able to contact them. We also have a sort of technical working group that is, again, uses the science working groups as input for what needs to be prioritized within the technical working group outside of maintaining the instrument. And so we have Martin Dyer, who leads the technical working group. We also work on scheduling and strategy, so how best to optimize the limited amount of time we have from both facilities. But we also have classification working groups, external follow-ups, as well as outreach and public engagement. And again, I'll leave the names up here if you wanted to contact them. So now we'll go through some highlights of GOTO. So I wanted to start with the main goal, which is the dedicated follow-up of gravitational wave events. And this was during 04 event where we were basically listening all the time to every event that came through. And so here's just a brief highlight of the challenge of doing this gravitational wave follow-up, where we have the luminosity distance in log scaled and the 90% sky area in square degrees, where in this very dark blue, we have majority of them are binary black hole events, which aren't expected to have an electromagnetic emission component associated with it. But you can see down on the bottom at very close by distances, there were some potentially interesting binary neutron star events, some neutron star black hole events. But the sky area coverage that they occupied was the 10 to the 3 to the 10 to the 4 sort of scale. And so this really definitely motivates the reason why we need to maintain these wide field instruments, particularly as discovery machines in the early times, which helps to identify candidates within the contaminant, where then those discoveries are then passed off to other facilities who can then characterize them in greater detail, particularly the LSST, for example. So just some highlights of what we did and achieved over the O4 run. We received and processed 5,430 super events that were released by LIGO. This includes 29 retractions. And so here we have it split over by run. And it was roughly the same number of significant events that were coming through from each stage. We received about 7 per day that we had to vet and understand and prioritize, where I think in the latter stage we started to relax these requirements, and I'll go into why, at least the motivation for why that is. And so of the 255 significant super events that eventually came through, GOTO has targeted observations for 163 of those. And what we have here is the number of visits for all targeted gravitational wave events. So these are for all 163, where some of these received a lot more coverage over in this patch in the north. But we managed to get roughly full sky-ish observations over the whole O4 observing run. And what we saw was the latency of our O4 follow-up observations was roughly the time from the event trigger to our first observation. Here you can see the CDFs of that, where the median amount of time from the event trigger to when we got our first observations was about 3 hours. And then when we received the alert to our first observation, it was about 0.09 hours. That's the median value. So we are rapid. So basically, yeah, once we receive the alert, we are able to rapidly follow them up and get on sky. And so I think one of the biggest questions, at least for me and one of the science drivers in designing the survey strategy and our follow-up plans, was this sort of unknown feature in the cumulative detections of gravitational wave events. And so here we have, all the way from the first observing run, an incremental gain in the number of events that we found until we hit O3, which we started to increase. And then in the O4 area, you can really see that it took off. What drove a few questions, at least for me, was what happens in O4B, what happens in O4C? Does this line actually continue? Does it fall over? And so there's a lot of discovery space, at least I think, in this, that once we get the candidates to come through, and maybe the gravitational wave transient catalog and LIGO has processed this data in more detail, then we can potentially pull out an unexpected signature. And so what we ended up doing was we modified the strategy. So I'm going to go back one slide. So what we ended up doing was, starting at the O4C in the second half, what we wanted to do was particularly target this space, sort of between this red line and the dash of what was observed, in the potential hopes that what was found within that sort of low latency data set were particularly interesting transients. And in the absence of identifying any particularly interesting transients or bona fide detections of neutron stars, we could start to try to place limits on the rates given our observations in a systematic manner. So here was our real-time follow-up strategy. We modified the strategy at the end of O4C in order to specifically target those lower threshold gravitational wave events. And so, of course, if these events were missed during our earlier iterations of our follow-up strategy, because we set quite strict thresholds on the false alarm rate and the significance as our main decision criteria, but with the premise that potentially these low threshold events can be, even though they are more likely to be just noisy gravitational wave artifacts, they can lead to some surprises. And there's been a few instances of that, particularly in early 2020, there were 2 potentially interesting neutron star candidates. In addition, we also perform serendipitous coverage. So here we might have delays in our targeted follow-up response due to operational challenges. So due to weather, scheduling conflicts, false positives, maybe the network went down at some point. So if we were to just take only our targeted observations as we are starting to perform all of the other target of opportunity alerts or simultaneous events that are coming through, what we decided was to do a serendipitous coverage method where anything within the time range of -5 minutes to +7 days, we would count towards that coverage. So while we targeted only 163 events with the names attached to that event, the serendipitous coverage ended up giving us at least, over 4,800 events with at least 10% probability coverage. And so this work is ongoing and hopefully due to be published soon on the overall statistics of that data set with the intention of releasing this as a public data product as a legacy data set to try to understand these detection rates in more detail. And I also wanted to highlight another method that we're approaching for our gravitational wave follow-up is that a lot of these events that we're picking up, in particular our design of our gravitational wave follow-up strategies, is that oftentimes we're really inundated with single candidate events, just single data points at one moment of time as a blip. And so, it's this kind of idea that could there be a way to improve and gain information out of this? And so what was developed was this Bayesian ranking of gravitational wave and EM candidates and a joint method. And so what it was that not only do you have the position, but you can associate that with a potential host galaxy and to try to understand whether or not it's associated. And so I'll leave that up as for those who may be interested in viewing this, but this is going forwards in a way to prioritize the often thousands to tens of thousands of candidates that we receive as part of our follow-up strategy, particularly in the serendipitous coverage area. Okay, so I just wanted to highlight just a very few of these event candidates. Just one of these, this was a candidate neutron star black hole. This was 250206 DM. We covered approximately 71% of the sky map, and we started observations in about 3 minutes. And I think all in total, there were about 114 reported candidates, where one of our candidates was ruled out as a young supernova. I don't know actually. So what we have here is transient discovery. I think there's some formatting issues here. As part of our survey and our science response, what we have is, as part of our sky survey, in addition to the gravitational wave follow-up, is on the 2 to 3 day cadence, we have additional discoveries from supernovae, TDEs, blazars, lots of galactic variables, moving stars. And as part of this, we're able to start submitting candidates to the TNS with greater regularity, so hundreds to thousands per month. And so this was a particularly nice moment. I was selective in this. This was in January, or sorry, at the end of December 2025, where we were able to report over 1,000 that month, as well as discovering over about 1,100. And so this was in part due to some of the upgrades that we performed as regular maintenance. So mirror cleanings helped us gain a bit of extra depth, which led to an increased transient discovery rates, as well as some other minor fixes within our processing pipeline. And so what I want to leave here is just a brief overview of the summary, kind of improvements that we're planning, and what's the outlook going forward. And so what we have is that GOTO-Network is fully operational. We have 2 in the north, 2 domes in the south, so total 32 unit telescopes. Each mount set and each dome is about 44 square degrees, so about 90-ish square degrees per site. We get down to depths of about 20.5 magnitude. That's increased since we did some maintenance and some cleaning of our hardware. We're able to cover the sky about every 2 to 3 days. So the legacy 04 gravitational wave follow-up data set is in preparation. We have improvements coming to the software, hardware improvements. So we're planning upgrades for CMOS sensors, additional filters. We're also performing some responsive software for real-time quality adjustments. And I think one of our most exciting sort of improvements that's upcoming is that we're currently working on a force photometry service, which will enable GOTO data to become public. And this is being led by Dan Jarvis out of Sheffield. So this is under active development, and hopefully we'll be able to make a public announcement for in upcoming few weeks to months. Okay. This was part of the responsive quality assurance system, but I'll leave this here. And I just wanted to say thank you very much.
Thank you so much for presenting this amazing work. You show that it's a lot of work, and it's very exciting to know that all this data is being collected. Thank you.
Thank you.